Hi, my name is Christian Cardozo, and I'm the lead instructor for Medlytics this year, 2021. In Medlytics, which is short for medical analytics, we teach students to apply machine learning approaches to real medical problems. Things like predicting hypothyroidism in patients, using physiological signals to classify sleep states, and even spotting cancer from mammography images. Using these problems, we can motivate and demonstrate a wide range of machine learning approaches, including decision trees, convolutional neural networks, and support vector machines. So now let's turn it over to our students for their final presentations. Wonderful, and I'm now making group number, the Coughify group are now panelists, so it looks like they're coming up now, and they will be doing a live presentation. If all goes well, we won't use the video. Let's see. Yeah, looks like you guys are here. Drew here as well. Yeah, all right. All right, go team. You guys ready to present?
Yeah, can you hear us okay?
Yes. Well, I can hear you, Shri, but I'm sure it extends to the others.
Hello everyone, so we're Team Coughify from the 2021 Medlytics course, and in this project, our goal was to create an affordable diagnostic tool to detect for COVID. To the left, you can see our logo, and as for us, my name is Zembin.
My name is Drew.
My name is Aryan.
My name is Shri.
And my name is Saket.
So on this slide, you can see our table of contents. So in the next slide, we're going to talk about the problem overview, followed by how we pre-process our data, followed by a basis of neural network and our model and results. Lastly, we're going to have a demonstration of our web app. So problem overview. As we know, here in the United States, COVID-19 tests are really accessible in many places. However, that is still not a privilege offered to many citizens in third world countries like India. With that in mind, we wanted to offer a cheaper and more accessible method to test for COVID. By utilizing machine learning, we can create a model to predict if someone has COVID, is symptomatic, or is healthy using a recording of their cough. The end result, Coughify.
Our first step to solve our problem was to find a dataset. So the dataset that we found is called Coughify, which is a crowdsourcing dataset containing 20,000 entries of different coughs. So Coughify has little to no bias since it represents a wide range of subject ages, genders, geographic locations, and COVID-19 statuses. Each of the 20,000 entries comes with its own label, either 0 for negative for COVID-19, 2 for positive for COVID-19, or 1 for symptomatic, which means there are some symptoms of COVID-19, but the patient doesn't necessarily have COVID-19. So for our inputs, the sound files were in the WebM format, and the labels that came with the cough files were in the JSON formats. Before we go to our model and pass in our data, we needed to pre-process our data. So the first step for pre-processing the data was data extraction. So out of the 20,000 different coughs in Coughify, there were 1441 usable audio files that we could use. And each audio file we converted into its 40 MFCC features to easily put into our neural network. The second step was data cleaning. So some of the samples had missing data or data was non-rectangular. And as a result, we just had to omit some samples so that our model would work. The third step for pre-processing our data was to clean our audio files. So each of the coughs had different lengths from some were longer, some were shorter. So as a result, we scaled our audio file to 862 frames, using either padding to increase the length or cutting down the audio down to 862 frames. Our fourth and final step to pre-process our data was data balancing. So as you can see on the bar chart to the left, we had a different amount of healthy, COVID-19, and symptomatic cases. And in order for our model to work best, we needed an equal amount. As a result, we used SMOTE to equalize the number of samples, and we got our data in the bar chart resulting on the right.
Next up, we have feature engineering. So feature engineering is essentially the process of deciding which features in the audio the model should use to learn off of. For this project, we use the Mel Frequency Spectral Coefficients, or MFCC, as our collection of 40 features. So this spectrum is commonly used for audio classification in the workplace because it's organized non-linearly to better represent human sounds as compared to the generic spectrum, which is linear and does not account for nuances in human speech as easily. So in our project, we use a neural network as our model algorithm. But what are neural networks? To start, neural networks are a type of machine learning algorithm that are designed inspired by the brain. Similar to how the brain has interconnected neurons that pass information to and from each other, a neural network is a collection of computational neurons passing information to and from each other. You can see here that after the pre-processing that Dhruv mentioned, the data passes in through the input layer, moves on to the hidden layers, and then exits in the output layer. While the data is passing through all these layers, the model is being trained according to various weights. Weights are essentially how heavily one node or characteristic in the data set should be weighted in that connection. So it's essentially just a measure of how important one node is over another. And lastly, loss is the shorthand for the loss function, which is a measure of error. The purpose of all neural networks and all machine learning algorithms is to minimize the error or to minimize the loss. Now, one of the hardest parts of creating a neural network is optimizing this neural network. And the purpose in optimizing a neural network is to increase model accuracy. The reason it's so hard to optimize is because there are so many parameters that you can change. For example, here we have a few listed. Depth and nodes we touched on in the last slide. The optimizer is essentially what's editing the weights and the learning rate to minimize the loss. The activation function is the mathematical function and the mathematical equation at each node that the model is learning through. The learning rate is how fast the model learns, and the batch size is the number of trials and the number of the batch size is the number of samples, and the number of epochs is the number of trials. But all in all, optimizing a neural network is a lot of trial and error. It's more of an art than a science, and with the more experience you have, the more intuition you'll gain.
So we've discussed neural networks and some of their parameters, and now let's move on to discussing our type of model. We feed a 3D array of our MFCC feature data for each patient into a convolutional neural network, which is a specific type of neural network that we used for two main reasons. CNNs are really good at extracting patterns that are translational invariant and have spatial hierarchies. In our use case, our CNN is able to identify various patterns relating to the strength of a cough that aids in our model in its classification. Second is that CNNs are very computationally efficient, which promotes their universality and enables us to run diagnostics on mobile devices, which is especially important considering that our target users, who are such as people in India, probably only have access to phones. These factors made CNNs a very attractive choice and influenced us to try them out. Then, at the end of our model, we reach our final layer with 3 neurons that outputs whether our patient is healthy, symptomatic, or they have COVID. Let's move on to discussing our architecture. We began our model with 3 convolutional 2D layers that identify the important features in our data. Then, in our max pooling layer, our model extracts the most relevant data and passes that on to our dropout layers, which help generalize our model and make it so that it can be properly used in real-world scenarios. Next, the flattening layer is used to reshape our data so that it can be better processed in our final layers, which apply various weights to our data that helps us reach our output, which predicts whether a patient has COVID-19, is symptomatic, or they're healthy. It is important to note that other important factors that influenced our model are our optimizer and our learning rate, and we decided on these models simply because they provided the best performance. We utilized Atom, and our learning rate is 0.001, which is a relatively moderate learning rate. Finally, our model results. Our training accuracy is 99.7%, and our validation accuracy is 98.3%. These are really high results. And our validation accuracy, which acts as testing data to assess the performance of our model, is performing really well. To confirm our results, we also assessed our AUC, or area under the curve. This is another performance metric that measures the ability of a classifier to distinguish between various classes, and in our case, it distinguishes between healthy, symptomatic, and COVID-19. The maximum score an AUC can give is 1, which refers to a perfect model. And because our AUC is 0.985, this tells us that our model is performing at a very high level. Finally, in the bottom right, a color map of our confusion matrix is shown. The diagonal of blue squares represents true positives, or the number of times the machine learning model was able to correctly predict the patient's disease. Thus, we want to maximize our predictions in the blue squares and minimize our predictions in all others. Our graph shows that blue squares represent areas that our model predicted a high number of predictions, and the white squares are areas with a low number of predictions. Thus, it is apparent that we are able to maximize our true positives and minimize our false positives, indicating our model's high performance. Our stellar results across multiple metrics tell us that our model performs very well, and we are even able to perform better than professional researchers who also worked on this project.
So once we were able to see the accuracy of our predictions, we decided to move on to our web app, which you can see later on. So we have 3 future directions after the web app. One is incorporating more diseases. So other diseases such as influenza and pneumonia can be detected from coughs according to clinicians. So we plan on extending our app to these diseases so we can have a broader clinical range. We also plan on writing a research paper detailing our unique methodology as well as our great results on the COVID dataset as well as the other datasets that we looked at. And then afterwards, we plan on developing a mobile app so we have a broader reach to those who only have a phone and cannot access our web app on their computers. So as mentioned earlier, we decided to create a web app so our diagnostic tool can be publicly accessible. In the future, the app can be implemented in areas where disease diagnostic testing is not very accessible, and you can access the web app with the link below. And now we're going to go into a brief demo of the app. So this is our web app. Basically, you could either submit a recording of your cough or record a cough on the website. So first, we have this sample of COVID positive audio that we got from a data set that we didn't use for training and testing. So this is from a random data set on the internet. So we're going to drop the file here and submit. And once we submit, the model predicts from that file. And it outputs the probability for each class. So as you can see here, the probability of it being COVID-19 is 99.7%, which is pretty high, and it's pretty confident that it's COVID-19. So it shows that our model is performing pretty well. So next, I'm going to cough, and I'm healthy. So let's see how it does. Now I'm going to submit the recording. And it outputs that I'm healthy with a probability of 98.1%, which shows that it's pretty confident and accurate in its predictions.
With that, thank you for listening to our presentation. Are there any questions?
All right, I think I can get started. Well done, guys, on your presentation. Very nice application. So did you guys experience any overfitting? And if so, how did you avoid that in your model architecture?
So we did experience some initial overfitting, but we added more dropout layers with a higher dropout rate, which reduced the overfitting significantly.
So dropout layers works for you?
Yep.
Okay. I think, Dana, do you have a question?
Yeah, so first of all, congratulations on getting this application out there. I just wanted to ask you about like the challenges, right? You're working with audio files. What were the major challenges that you've encountered? And in the future, like what, with crowdsourcing, the crowdsourcing application that you have, how do you, plan to acquire more kind of crowdsourced data?
I can take this one. So we ran into one large issue using audio data was that we were trying to understand what engineered features to extract and how they would sort of work with our model. So two things that are important to do is that first we decided on using MFCC, which is a common engineered feature that's used in audio. And then the second thing that's important to realize is we used a CNN for audio classification. CNNs are usually used in image classification, and so it is an interesting choice that we used a CNN for audio classification. However, we simply decided to use the CNN because we were able to achieve high results. And so those two considerations were things that we had to do trial and error with, and those were things that we sort of had to overcome in order to achieve our final model. And then the second part about expanding to more data sets. Right now, we've done some initial research. We still need to do more, but we've found some data sets that have been standardized, some audio data sets that have been standardized across coughs. And so we plan to expand our model using those data sets and then implementing like a real app that will enable people to like give their coughs, and then that can be used to expand our data set even more. So yeah.
Thanks,
And
Ariane.
then,
Yeah, go ahead.
Then just to add on to what Ariane said, another kind of challenge that we ran into, which might not be specific for audio classification, was our SMOTE data balancing. So we realized that like we were unintentionally biasing the data because our data set came with like 70% healthy results versus like 30% the symptomatic and COVID results. So when we did have to put it through the data balancing via SMOTE, we ran into problems where like the organization of our data was really complex and not very clean when we extracted it just from the data set, in that we had arrays all over the place. It was not clean at all. So we took a few hours to like sit down, clean all our data, and then make sure it was optimized and pre-processed before we ran it through trained our model.
Yeah, I think, even with SMART, right, you have 3 classes, so you have to kind of balance them all. Yeah. All right. I think that's all from my side.
I'm curious, can you guys play back the audio for the person who was likely to have COVID?
Yeah, sure. I don't know if it'll share the audio through the Can you hear that?
For a moment, I thought it was someone in the audience, and then oh, that's right, he's playing the cough. Oh, cool! Wow, it'd be really cool, yeah, just to sit down and listen to the 2 clients. This is really, really cool. Well, thank you guys. All right, any other questions from people?
Actually, one question comes to mind. So, you got a lot of data and you're planning to continue to get more. So where did you get this data from initially?
So we got it from the Coughify data set, which is collected by a group of researchers in Switzerland. And they basically got it from a website where they made their own website where people can submit audio recordings of them coughing, and they can label as whether they're COVID or healthy. And they also got a bunch of clinicians to verify those diagnoses. And then there's also a couple other data sets, like there's a COSWARA data set that we were experimenting with, but we decided not to use it because the file size was too large. I believe the data set was 16 gigabytes, and it didn't seem feasible when we had pretty good performance on the Coughify data set.
Yeah, I think it's very important to have clinicians, right? Even just symptomatic versus actual COVID patient, that's even hard to, kind of diagnose. So well done.
Yeah, Thanks, you guys. All right. So if that is everything, let's go ahead and pass it off to the next team. Yeah, congrats, you guys. This is really, really cool. We're now going to pass it off to the next group. I don't know if you have a way of not making yourselves panelists, so I'm going to go ahead and, I guess, demote all of you. All right. I guess it just has to be that way. Change to F&B. Saket, goodbye, Saket. See you soon. True. And are in. All right. Who made it? Who's left? Okay, so we've got a presenting team. If I could ask everyone in the class to rename yourselves such that you have your name, sorry, your team number, dash your name. It will make getting the teams selecting people to make panelists even easier. So if you are able to rename yourself as like, 2-Christian Cardozo, for example. And I got a message. Oh, you can't if you can't rename yourselves, then I guess it was worth a shot. But it's okay, we have everyone's name. All right, so now we have team number 4, our second team to present today. And I believe they're all panelists. Team 4.
Hello?
Oh, there we go, okay. You all set, Jasmine?
Okay. Is my camera on?
No.
There's no option for me to turn it
no.
on.
Oh, hang on. I think I know what I got. Oh, sorry, hang on. Promote panel. I thought I had promoted you. Try and give it a shot now.
Okay.
Okay, there we go. Yeah, that's my mistake. I didn't know what I did or didn't do. Okay, all set.
Okay.
All right. Hello, everyone. This is our final BWSI Medlytics project over ocular disease recognition. We're team, I'm Madhav Ram, and my name is Divya Potavajula.
I'm Jasmine Jung.
I'm Marisa Espera.
And I'm Ismail Forrest.
So first, we'll start off by giving a brief introduction to our project, and then we'll move on to data processing, and then we'll talk about our model, and finally, we'll conclude with our results.
First up is the introduction. So some objectives for our project were to create a model to properly classify retinal scans into one of 8 categories, to improve classification metrics for diagnosing optical diseases, and to create an accessible application to help ophthalmologists and patients. Some optical diseases that our model was trained to find include glaucoma, which is when fluid from the eye doesn't drain properly, which increases the pressure on the eye and damages the optic nerve, blocking someone's eye vision. Cataracts, which occur when the lens of the eye become clouded, preventing light from properly traveling through the lens. There's also hypertension, also known as high blood pressure. Sometimes the heart works really hard to push blood through the blood vessels, but certain causes like smoking and high cholesterol make it really hard for the heart to pump blood, which increases the blood pressure. And pathological myopia, which is extreme nearsightedness, when someone is so nearsighted that their eyes are elongated and no longer shaped like regular spheres. Furthermore, we have diabetes, which occurs when your body doesn't make enough insulin or doesn't use it properly, along with age-related macular degeneration, which is when parts of the macula get thinner with age.
Our group spent the majority of our time when working on this project finding a way to pre-process the data. The public data set, which we had taken off of Kaggle, contained a folder full of training images and test images. However, they were not all linked to the labels needed for classification. Within the data set that we were given, though, some text features that were included were age, sex, and image diagnostics to help classify the images and the patients within the data set. Like the images on the slide show, image diagnostics explain what the image is showing, including fundus, cataracts, and drusen. On the left of the slide here, the original data frame we were given included the data and image paths for the left and right eyes, but they were not put together in a way that would allow us to easily access the data for the left and the right eyes for each patient. So we had to manually fix the data frame through Excel and understand Excel's built-in functions to remove patients without information for both eyes and also bring together the left and right patient data. With this scrub data, we started pre-processing by loading and storing full JPEG images from the paths. However, with this, we ran into our first problem, which was running out of memory. We had to move to different collaborative data science notebooks in order to combat the problem of running out of RAM, until we realized that it would be better to store the path to the image instead of loading and storing the full image because it would use less memory. So instead we kept the image paths in a dictionary, which would call the information when it would be used in the model, and then it would be cleared once it's no longer in use. Another issue that we ran into was having dimension issues when we started running the data with the model, meaning that what was being inputted into the model wasn't compatible, mostly because our images were RGB images instead of grayscale. They were also not lined up with the image classification labels used to train our model, but we were eventually able to get it going, allowing us to officially start training.
So once our data had been pre-processed, we're able to start creating our model. So neural networks are a machine learning algorithm inspired by the brain in how information is passed from neuron to neuron. Similarly, in neural networks, information is passed from node to node. So it takes in inputs and gives out the corresponding outputs. And within the input and output layer are a series of layers known as hidden layers. And in these layers, the model is essentially doing the learning. So models are trained first when the data set is split into training and validation data. So our data set are the images from Kaggle. The training data is then passed through the model, and the model learns using this data. And the validation data is used to check how the model is doing based on what it has learned from the training data. And after multiple runs of this, a final test is done through the testing data. So optimizing a neural network basically means making sure that our model predicts the correct output for each given input. There are a variety of parameters to do this, such as network depth, which is the number of layers, the number of nodes, learning rate, which is how fast our model learns, optimizer, which edits things like the learning rate to minimize something called loss, which is an error function. Activation function is a mathematical function that the inputs are passed through. Epoch size is the number of trials, while batch size is the number of samples. So due to the sheer number of parameters there are and the variety of datasets, there really is no best way to train a neural network. So this is a few key points from our model over time. So we trained our model based on something called AUC, which is the area under the curve. And this metric takes into account true positives and false positives. We used AUC as our metric for optimization because we wanted to make sure to maximize the true positives, and also AUC was better fit to our data. We started off with an AUC score of about 80, and after editing a variety of parameters such as optimizer, learning rate, depth, epoch, and batch size, we were able to attain an AUC score of 90. And given that the max score is 190 is pretty good. So our model is something called a convolutional neural network, or CNN, and this is just a special type of neural network which has convolutional layers. We had a base model called VGG16, and this is a pre-trained model, meaning that it's already been tested on millions of image samples, making it a good baseline. On top of this, to make sure our model is detecting a variety of features, we added 2 convolutional layers. And to sort of intelligently downsize our images, we added 2 max pooling layers. And then to make sure our model is not overfit to the training data, we added 2 dropout layers. And what this does is basically make sure that our model is more versatile in that it's able to perform well on other data, such as the validation or testing data. And then the flattening layer is to reduce the dimensionality to 1, so we can fit it through the output layer. And a few other specifications of our model include the learning rate, epoch size, batch size, and type of optimizer.
Okay, so now on to our results, where we'll talk about analysis, website prototype, and future implementations. So first is our model performance. The first 2 graphs on the left and the middle show our model loss and AUC versus epochs, which is the number of times that we trained. Our model loss grew smaller over time, and our model AUC grew larger, meaning that our model had trained an increase in accuracy over the trials. Our third graph shows our multi-class model's area under the ROC curve, in which we had a score of 0.9. So now on to our website prototype. So first, we have the site where ophthalmologists can upload patient data, such as name, biological sex, birthday, and their diagnostic keywords, as well as images of patients' left and right retinal scans. After submitting, they'll be taken to a page that, after submitting, they will be taken to a results page where they can view the patient data and edit as needed. As an example, we have James Ross, who is a male age 68, who had a right retinal scan result of cataracts and a left retinal scan result of normal. Our website also provides treatment options below the diagnosis. So back to our presentation. Next is our future implementations. Our future implementations include improving the metrics and generalizability of our model, and we would also like to add more features and data to train our model for higher accuracy. Next, we would also like to classify more diseases. Currently, we have the other class in which we can add. Finally, we would like to create an app to improve the accessibility of our project for medical professionals. And before we finish, my team and I would like to thank the BWSI Medlytics staff, Christian, Shashank, Lama, Dana, and Mira, as well as the staff in general. Thank you for the wonderful experience this summer, and thank you for listening.
Thank you, guys. This is really, really cool. And I think your project this is the project that most shows the importance of getting the data in the right state to process and the importance of that. So really, I mean, you've learned a hard life lesson way ahead of time, it seems.
All right, I guess I can get started with some questions. So in terms of the left and right images, did you have an equal balance of both?
Originally, we did not, so that was why we had to go into Excel and filter out the data, because some patients had right images or they didn't have left images, and they had left images and no right images. So going in manually into the data frame, we were able to equalize the amount of patients and make sure that each patient had both left and right image data.
Okay, and then in terms of like the features, what features that you think you'd want to include more in the future, you know, as you progress with the project, either, you know, in the images, age and sex and so forth?
Something that I had noticed about the data set is that it doesn't really include anything about race confounders, because race is a big issue as far as making sure everyone can use the model and also have data that is correlated to their specific biological features regarding race. So something including race and maybe even location would be very helpful in the future.
Yes, definitely. Race is a huge factor that we all have to take into consideration when training our models. All right, that's all from me.
Well done again. I think the question that I have for you guys is in terms of like validation, right? Or either internal or external validation. How did you validate the performance of your model?
So basically, we had a total of about 3,500 images. And after taking out a few that didn't have left or right, like Risa had explained, we were left with still close to 3,500, but just a little below that. And we split our data with a bigger set of training, and then so that our model was able to learn more and get more information from that set. And then we used the rest for validation data. But the only issue with our data set was that we actually didn't really have a testing set. So we actually were testing and basically validating with the same validation data, which is one like limitation to our model. But essentially, our validation was just right through the model, just as the training had.
And one other thought here is in terms of pre-processing, right? You were working with images. Did you consider maybe adding, structured data versus the imaging, which is unstructured, into your pipeline? And what challenges did you have in pre-processing? Like, how did you tackle those pre-processing problems there?
So we thought that would be a part of our future implementations. And so we would add structured data such as patient demographics. And for now, we have our image model, which is just using the left and right retinal scans. And so we also would like to add structured data regarding like patient diagnosis. And so for now, we actually ran into one problem when doing that, is that we couldn't find a way to combine our two data sets without causing an error. And so that would just have to require more research, and that will be in our future implementations for our model.
Yeah, so it looks like with imaging, was there any challenges there in terms of pre-processing? Like, did you have to filter it, or was it given already pre-processed for you?
It was not already given pre-processed, so that was a major issue for us. And especially because it was a full JPEG image, it caused a lot of error with memory because the quality was so high. So we had to decrease the image size and make sure that it could be filtered through the model. So that was a big issue and something that we spent a lot of time on.
Also, that's what our name comes from, out of RAM, because we ran out of memory when going through those big images. And so we just had to downsize them so we could go.
All right, thanks, Jasmine. Thanks, Risa. Thanks, Divya and Izmir.
Yeah, thank you guys. This is really cool stuff. We're gonna go ahead and move on to the next team, which is team number 3, and they are presenting a video. It's Team Hack Overflow. Shashank will be sharing their video presentation, and I will go ahead and make them panelists. And it looks like we have one more question in the Q&A. If one of the panelists from this team, from I'm Out of RAM, can answer that in text, that would be great. Ready when you are, Shashank.
Okay, here is Group 6 Hack Overflow's final project presentation video.
Hi, our project is detecting colon cancer, and our group name is Hack Overflow. So here we can meet the team. My name is Pranav Devabakuni.
I'm Sam Dillon. I'm Mark Rosian.
And I'm Wei Wong. So our project is split into 4 different categories, and these are the introduction, data processing, model training, and the results and analysis. So moving on to the introduction, what is colon cancer and who does it affect? So colon cancer, as said in its name, occurs in the colon. And if you look on the left, there's a human diagram where you can see all the different organs. And there's a little target of where the colon is actually located in the human body. Colon cancer typically tends to affect older adults. So when people start to hit the age of 50, physicians start to actively screen for colon cancer. Colon cancer is also the second deadliest cancer in the world. I believe in the United States, last year it caused around 60,000 deaths directly. And the reason why our project is so important is because if colon cancer is diagnosed early, survival rates are much, much higher. So the importance of our project is that our machine learning model could be used to help augment clinician diagnoses. In some cases, it could also be faster to just use our model to get a diagnosis directly. And our model may be able to help decrease human error. As some of you may know, colon cancer is the second most misdiagnosed cancer in the world. So our model may be able to pick up on small details that human physicians would normally miss.
So our course in this project are on machine learning, but what is machine learning? Let's start at learning in general. One definition of learning is trying something, making mistakes, and using those mistakes to improve. And machine learning does exactly that. It makes a prediction based on data and then receives a value representing how far off its guess was, sometimes called an error or loss, which it then uses to adjust its guessing mechanics to make a better guess the next time. Now let's talk about how to make a machine learning model. First, you need to pre-process your data. Second, split the data into some you can train on and some to test with. Then further split some of the training data into validation data to test your model on as it trains. Then select the right model for your data, train the model with the training data, evaluate the model on the validation data, and test the model on the testing data that hasn't been touched.
So the next section will be about data processing. Let's first take a look at the data set that we'll be using. It contains 10,000 images in total, which is about 1 gigabyte in size. The images are about tissue samples that can be used to distinguish between positive and negative cases of colon cancer. The images are 768 by 768 RGB JPEG files. And once we know what the data set is about, we'll need to import the data. Due to the large size of the data set, we'll only be using 5,000 out of 10,000 images for this project. We use Google Drive to import 2,500 images for each of positive and negative cases. The next step is recycling. 768 by 768 is too large a dimension for training, and it will take a long time to train the model. So we want to downscale the images to 256 by 256, as shown in the screenshot on the right. Now, to prepare the data for model training, we need to separate them into different groups. We first split the data into training and testing sets, and 20% of the data, or 1,000 photos, went into the testing set, while the remaining 4,000 went into the training set. Next, we split the training data into training and validation sets using the same 80 to 20 data. Testing set is for final testing of model accuracy, whereas the training set will be fed into the model for training purposes, and the validation set will be used to verify the results of each round of training during the model training process.
So next we're going to talk about how we made the model. So for our machine learning model, we decided to use a convolutional neural network. So first, what is a neural network? A neural network is a model that consists of nodes, which are all these little circles here, and they're all called artificial neurons. And they're somewhat based on the structure of neurons in the brain in like organisms. So each neuron receives a signal in the form of a number from the previous layer. Each layer is the vertical line here. So it processes that signal with a function that changes as the model is trained, and then it outputs that signal into the next layer. So a convolutional neural network is a specific type of neural network that is specifically designed to process images. So before being run through the regular neural network here, the image, which is in the form of a 4-dimensional array, so this image is convoluted, which is a matrix operation, then it is max pooled, where the largest value from a region, such as this 3x3 square here, is selected and replaces that region in the new matrix. After max pooling, it is flattened, where the data is converted into a 1-dimensional array, and then the flattened data is being run through the remaining regular layers, also known as dense layers. So there are 2 steps to creating a successful neural network. You need to build a decent base model with the correct layers, and then you adjust that model by running it and seeing what must be improved. So for building the model, at first, our group attempted to use transfer data learning for a network, which is when you use an already existing model on a different data set than what it's trained for. So for models, we used VG19 and Inception, for example, but we really didn't have success. We couldn't achieve an accuracy above 55%. So then we found that switching to the traditional neural network where we build one, give us much better results. So we did that. After some tinkering, we found that the best parameters would be 3 convolutional layers, 2 max pooling layers, 1 flattened layer, 8 dense layers, and 1 output layer. So for training the model, we used our training results to continuously update and improve our model. We needed epochs, which is 1 full run through the data set of the neural network, and a batch size, which is the number of training samples before the model updates itself, that show the correct accuracy of the model while not taking too long, and also avoids overfitting, which is when the model becomes too used to the training data and is accurate with the training data, but not with other system data. So we decided that the best numbers for this would be 10 epochs and a batch size of 150.
After training our model, we evaluated it with a few metrics. The first is a confusion matrix, and the second is the area under the receiver operator curve, or AURC. A confusion matrix shows the predictions of the model against the actual outcome, which in our case is the positive or negative diagnosis associated with each image. True for our model means the patient has colon cancer, and false means they don't. So if our model predicts that they do have colon cancer and the patient really does have colon cancer, that fits the true positive category in the upper left of the matrix, and so on. Our model outputs a probability between 0 and 1, but the confusion matrix doesn't accept continuous values. So we convert the probabilities into either 0 or 1 based on whether it is above or below a threshold that we set. For the specific confusion matrix, the threshold is 0.5, and the threshold can be set at other values to emphasize certain parts of the confusion matrix. The next metric we used is called the AURC, or area under the receiver operator curve. The RC combines the output of a bunch of different confusion matrices with different probability thresholds. We can then look at the area under this curve, and the closer the value is to 1, the better it is at predicting true cases as true and false cases as false. So for our model, we wanted a high AUC and even prioritized AUC over validation accuracy because it's a more universal metric. We also wanted a low false negative rate so that patients aren't told they don't have cancer when they actually do, because that's very dangerous. So finally, here are the model's accuracies. We got a 0.963 AUC, which is very close to 1, so it performed well on that front. And our confusion matrix looks good too. You can see that its predictions were almost always right, and it never told the patient who didn't have cancer that they did, as you can see in the bottom left. We also had a 6.8% false negative rate, which is relatively low, but we definitely still have space to improve there.
So the next step for our project would be moving from binary classification to multi-class classification. So ideally, our model would be able to determine whether you had stage 1, stage 2, stage 3, or stage 4 cancer in the future. Another step is moving our model onto a web app. So on this web app, patients could potentially submit pictures, and our model could tell them the probabilities of being diagnosed with a certain stage of cancer. And then I think our final step would be to consult medical professionals. So we want to see if our model would hold up to medical industry standards and see if there was anywhere we could improve our model. Thank you. And if you have any questions, feel free to ask.
Well, congrats, you guys. Thank you. We have time for one question if someone wants to go.
So I have a quick question. When you guys were downsizing your data, what was the thought process behind choosing specifically 256 by 256 for the final image size?
I got this one. So based on a previous project where our size was around 300, we chose to start off downsizing our images to that size and then testing our model. And then we, because of time constraints and how long it took to load data and then train, if the images were larger, we tried make them even smaller to see if that would improve training time, so we could get more, we could try more variations on our model. And it didn't decrease accuracy, so we stuck with that.
Thanks, you guys. All right. Let's go ahead and move off to our next team then. Coming up. Oh, and congrats, you guys, again. This was all the presentations are very, very cool. We're now hitting up team number 5, whose name is work in progress, Sanjana, Dipti, and Dia. You guys can take it away.
Hi, and welcome to our presentation on 3D intracranial aneurysm detection. I'm Dipti, and my group members are Dia and Sanjana. So we're just starting off with a little bit of background on our project. So intracranial aneurysms, also known as cerebral or brain aneurysms, are thin or frail areas in brain arteries that can bulge and rupture, causing hemorrhages where blood goes into nearby tissue. Around 1 in every 50 people in the US have an unruptured cerebral aneurysm. Each year, about 8 to 10 people in every 100,000 people experience a ruptured aneurysm. Nearly 500,000 people die from brain aneurysms annually around the world. 25% of those with ruptured aneurysms die within 24 hours, and an additional 25% die due to complications within 6 months. With these statistics in mind, we feel that our model will be an effective tool to assist physicians in diagnosis of cerebral aneurysms in order to hopefully save lives. Next, we're going to talk a bit about our data set that we used. We trained our model on a publicly available dataset called INTRA, 3D Intracranial Aneurysm Dataset for Deep Learning. We specifically used the data for generated blood vessel segments that came from 103 3D full brain vessel models that were reconstructed from scanned 2D patient MRI images. There were 1,909 of these generated segments, of which 1,694 were healthy segments and 215 were aneurysm segments. Each segment contains data points for XYZ coordinates, XYZ normals, and labels. The coordinates provide locations in 3D space, and the normals are normal vectors, which are vectors perpendicular to surfaces at certain points. These normal vectors essentially show the direction of the surface. We edited the data to ensure that all healthy segments had a label of 0 and all aneurysm segments had a label of 1. The dimensions of our final data set were 2,314,162 rows by 7 columns. So here we just have a visualization of a healthy blood vessel on the right from our data. And on the left, we have a visualization of a blood vessel with an aneurysm. And the aneurysm is a small spherical shape at the top.
I'm Sanjana, and I'll be telling you about the model that we used to train our data. So before I talk about the final model, I'll tell you about the different models that we tested. So we tested a k-nearest neighbors algorithm, SVM, and also a neural network. So a neural net for the k-nearest neighbors algorithm, we can see at the top there's a diagram of a simplified version of what the computer was doing to the data. With k-nearest neighbors, there's a k number of nearest neighbors that the data belongs to. Our model conducts binary classification, and for either positive for an intracranial aneurysm or negative for the intracranial aneurysm. It's a supervised algorithm, meaning that it learns from the labeled data. And in that case, that was either positive or negative. And we also test about the neural network. If we go below, we can see on the right, there's an image of the summary of our neural network. So in our neural network, we had 4 dense layers and 1 flattening layer. And with the neural network, we actually got a pretty high AUC of 93%, but our k-nearest neighbors algorithm was actually higher with an AUC of 99.55%. So we ultimately chose the KNN model based on the metric of AUC, which means area under the curve. And this curve refers to the receiver operating characteristic curve. And on the left, we can see a diagram of that. The receiver operating characteristic curve plots the number of true positive rate against the false positive rate. And the AUC is the area under this curve. The dotted line is the line that represents basically a random chance, while the curve represents the actual model. And since our KNN model had the highest AUC, we chose it as the algorithm. And through optimizing the k-nearest neighbors algorithm further based on the AUC, we ended up on the k value of 10.
So as we mentioned or kind of alluded to, there are several different metrics that you can use for model evaluation. So you may think accuracy would seem like kind of an obvious metric to see how good your model performs. Accuracy more technically, is the amount of correct predictions over the total amount of predictions. And the problem, though, with accuracy is that it's only effective when you have the same amount of each sample type. So having an imbalance in the amount of each group can lead to a high accuracy because the model could just classify all samples into the group containing the most samples and achieve that percentage of accuracy. So we found that our data definitely had this imbalance between the size of our two groups. So we chose AUC, or area under the ROC curve, as our primary metric because it's far more resistant to this issue. Another thing we did was we generated a confusion matrix, which will show you the number of true positives, true negatives, false positives, and false negatives. So true positives are when the model predicts something as being positive and it actually is. True negatives is the same thing for negatives. False positives is when the model says it's positive, but it actually is negative, and false negative is the opposite. So the confusion matrix is particularly important to healthcare scenarios because having false positives, but particularly false negatives, can have far more serious consequences, both health-wise and costs and in terms of other factors. So we additionally found something called the normalized confusion matrix, which you can get by dividing each row element of your confusion matrix by the total of that row. So this will give you the percentage of predictions for each class that the model made for a certain true label out of all the true labels for a specific class. And just a heads up, for our case, there's only two classes, positive or negative, because we're doing binary classification. So here you can see some of the metrics I was talking about. Here's our confusion matrix. So these are the actual numbers that were classified in each category. This is a visualization of those numbers. So here's our normalized confusion matrix, and you can kind of see what I was talking about earlier with how to generate that. And here's the visualization for that. And here's our AUC. AUC only goes up to 1, so we definitely had a really high AUC, so we're really happy about that. This is our ROC curve, and like it says, like the area under it is our AUC. And these are our trading and validation accuracies, just for kind of a reference. So as you can kind of tell, what we've been showing you right now is our website. So you can access this website if you're interested by going to 3daneurysms.weebly.com. And under this resources page, you have a lot of different things that we used and a folder to apply our model. So one thing that you need to know about applications of our model is that it works with, our model was trained on a very specific type of data. As we mentioned when we were talking about the data set, the people who created this data set did a lot of processing steps to generate 3D images and then segment them. So our model requires a very specific file type. And to begin with, these kind of image scans are not something that everyday people would have on hand. It's more something for physician use. But we realized that as of right now, our model isn't great for user work in any kind of web app or app. So what we did instead, though, is created a folder that contains our model in this Google Colab notebook that you can just kind of use for fun to test our model. So you just run the cells, and you can upload the files from the original data set, because again, this is just kind of to see what our model's doing. So I can show that to you. And so I am going to pick a file. So that our data was separated into folders based on being positive or negative for intracranial aneurysms. And what it will do is it'll tell you if it's positive or negative right here. So here the sample was negative. And so also on this resources tab are a link to the original data set. The portions of the original data set we put in our own separate GitHub repository. And we will link a demonstration video that kind of has this same presentation that we just gave you and the demo of how to use our model. This is our sources tab if you're interested in learning a little bit more. If you have any questions, please let us know, and thank you for listening.
So hi, I'd like to say amazing work, and the question I have for you is, what factors did you take into account, or will you take into account in the future to ensure the generalizability of your model and to reduce biases?
Yeah, I could take this question. I think one thing we probably want to do is make our model more translatable to other data sets so we can kind of do external validation and just overall make the model more usable to users, but like more specifically, like I said, physicians. So one thing that we could probably do in the future to understand that better is get a better sense of how the data set was generated and figure out if it's feasible to use those same type of scans to generate the same data ourselves and maybe implement that in our Google Colab file, and then the model would become more usable.
Right, thanks, Dia.
Wonderful. Congrats, you guys. Really cool work. We're going to go ahead and move off to the next team, which is Team Unnatural Language Processing, and they prepared a video that we will now watch on the screen.
Hello, this is our final project presentation from the Medlytics course. We are Team Unnatural Language Processing, which consists of me, Vivian, Jiwoo, Lucas, Ray, and Valentina.
So first, we would like to present our problem statement. Our problem that we decided to attempt to solve is that hospitals many times have a transcribed information about a patient, such as their age, their gender, and some of their symptoms. And our goal was to use these descriptions to classify each patient with a medical specialty, such as allergy or cardiologist. And our solution was to use a machine learning model and language processing to suggest such a medical specialty for each patient.
So here is some background information onto our project. So the first thing is natural language processing, which is also known as NLP. This is the field of programming that processes and analyzes large amounts of natural language data. So natural language data is data that is continuous, but is non-quantifiable, which means that it does not involve any numbers. That means it can be more difficult to process this because there is no computations involved. By being able to interpret human language, machines can help with many areas of online communication, anywhere from email, spam filters to translation software. Another thing that is part of our background knowledge is the recurrent neural network, or the RNN. This is a type of artificial neural network that can understand sequential data. Also, examples of this are like videos or sentences. Each iteration of information cycles through a loop, which means that each decision is based on inputs that are based on previous and post inputs. That means each input is based on previous inputs and those that come after.
Now we are gonna talk about how we develop the model. So before we creating our model, we first clean our data. So originally, our low data has around 5,000 rows of patient transcript, which is a paragraph of text describing the patient condition or medical history. So we cannot use our model with this data directly. So we clean it through the tokenization. So we filter punctuation spaces and transform each unique words into a number identifier, turns a sentence into a sequence of numbers. After tokenization, we condense classes from 39 classes to 11 classes. So it reduces the noise and improve our accuracy. Also with stemming and lemmatization, such as like painted to paint. And we also remove stoppers like the, and, or, is.
Next most important part of our model would be the embedding layer. This would take in those sequences of tokenized data that we just generated and then returns a multi-dimensional vector for each word. I think we used around 64 in our final model. These vectors would be slowly trained over time to be grouped together into those with similar sentiments. This would allow the model to group together words that have similar meanings in order to process them in a similar way. And it would be able to use them in the following layers. So the next part is the long short-term memory layer. This is a slight modification on the regular idea of a recurrent neural network. While a regular one would mostly take into account those of the most recent words in the sequence, long short-term memory layer is able to keep track of words far prior to the word it is encountering at that moment. This is done through a cell state, which stores information carefully controlled by different gates, and it enables information to be stored in the long term. This allows it to put words in a proper context, even if the context is in the sequence-wise far beyond where the current word is. And then the final part, or perhaps the most important, is the transfer learning idea that you can use a pre-trained model with pre-trained weights in order to incorporate them into the model that we're using. And this would allow it to have a bit more context on a specific field. In this case, we're doing medical data. So we chose a BERT preprocessing and embedding model pre-trained on PubMed articles. This would have it be more familiar with the medical context and have it be able to classify words that are more obscure or pertain to more medical ideas. And this would be added on to the LSTM layers that we discussed and some more densely connected layers before returning the final result.
Okay, this is all great and really interesting, but right now we need to stop and ask ourselves, how is the model doing? So we did an assessment of our model with visualizations. On the left, you can see a confusion matrix with predicted labels on the vertical axis and true labels on the horizontal axis. For class number 3, you can see that there's a lot of red in both the vertical column and the horizontal row, which means that there are patients being labeled as class 3 when they actually aren't class 3, and labels that are class 3 that aren't being predicted as class 3. Basically, it's making a lot of incorrect classifications. Also, on the right, you can see the ROC, or the receiver operator curve. And for this curve, we want the graph to be as much in the upper left corner as possible. And most of our curves are. However, for that red curve that you see, which is the surgery curve, or class 3 again, there's a very big gap between the left side of our graph and that curve. And that was something that we wanted to change. So in order to change this, we wanted to do some model stacking, which is using different models and combining them to get a better classification instead of having a one-size-fits-all kind of solution. We wanted to use a binary classifier to determine whether this patient is in the surgery class or not, and then use a multi-class classifier to kind of classify all the other labels. This is because surgery was the class that was being misidentified the most, and also it took up about 30% of our data set. So we thought this might be helpful. Unfortunately, through rounds of testing, we found that this actually wasn't a very good way of trying to improve our model and didn't really come up with any results, as you can see with these two diagrams. On the left, again, we have a confusion matrix, this time with only 2 classes, and the diagonal from upper left to lower right is correctly classified, but that 52 were rows that were actually surgery, but the model didn't detect that they were surgery patients. So this isn't great. Also on the right, for the ROC, for this classifier, you can see that for about half of the graph, the blue curve follows that diagonal orange line, which is the curve that would occur if our model decided classes entirely at random, which means our model didn't do very well for about half of that curve. So we decided to just stick with the multi-class model that we already had and try to improve that to get better results.
And finally, we have our results. Drum roll, please. So first of all, on the left, you can see our confusion matrix graph. The highlighted diagonal line across the middle is the part where our model correctly classified the medical specialties. And there's a pretty distinct diagonal line, so that shows that our model is relatively accurate. And so our testing accuracy is 54.8%, but while this seems low, high accuracies become increasingly difficult with multi-class classification, as we attempted to do. And so hence our classification was actually relatively successful, as you can tell by the ROC score and graph. And so our general ROC AUC score is 94.7%. And as you can see on the graph below on the right, all of the lines have pretty high accuracies and are covering the entire square and are pretty far from the diagonal orange line, which signifies if the classification was random. Thank you so much for listening. Any questions?
Congrats, you guys. We have one more team ready to go, and it looks like we have a cutoff at 11:50. So we're going to take all the questions at the end, and we're now going to bring up our final team, Heartbeats, Brian, Amaris, Yasmin, and Sharab. Ready when you are.
Hello, everybody. We are the Heartbeats, and this is our final Medlytics project on classifying arrhythmias. I'm Yasmin.
Brian.
I'm Sharab.
And I'm Amaris.
So we're going to briefly overview what this presentation is going to be about. First, we'll talk about what exactly is arrhythmia and what a brief introduction to machine learning, as well as how we imported the data and visualized it, trained our models, and finally our results and conclusions. So you may be asking, what is arrhythmia? Arrhythmia is an irregular rate or a heart rhythm of the heartbeat, causing it to speed up or slow down. So this can be caused by changes in heart tissue and electrical signals to the heart. So there is no question that the heart is one of the most important organs. An irregular heart rate poses a serious threat to the heart's ability to pump blood and synchronize its movements with its heart chambers, which can result in situations such as cardiac arrest and blood clotting. There are many methods of diagnosing arrhythmia, which are blood tests, chest x-rays, ultrasound, and echocardiography. But for our project, we wanted to use the most common diagnosis, which is the electrocardiogram.
By now, I'm sure you all know a lot about machine learning, but here's a refresher. When computers use machine learning, they are not explicitly told what to do by a programmer. Instead, they use algorithms to determine the best course of action. Unsupervised machine learning finds patterns in existing data. Supervised learning takes it a step further to make it predictions about new data. Our group decided to create a supervised machine learning model that would take an electrocardiogram data and classify it into different types of heartbeats, some normal and others with different types of arrhythmias. Our main goal was to improve the quality of arrhythmia detection.
So next we'll be talking about our data processing and visualization. We found a really great data set on Kaggle that we wanted to utilize. So we first downloaded and imported the data sets into DeepNote, which allows us to use, which is great because it allows us to have team collaboration on one notebook. However, while DeepNote is great for working together, it has a small fixated amount of memory, which slows down the process of training our neural networks. And for this reason, our group also created a Kaggle folder on Google Drive and to import a Colab notebook, which would quickly run our models. So here we can see the different classes in our given data set after generating 10 random samples. As you can see, the data set we chose is mostly populated with normal heartbeats. Each graph is showing the frequency of heartbeats over time.
So our first instinct when we saw these ECG graphs was to use a Fourier transform. So what is a Fourier transform? Typically, when you think of a signal, you think of something that looks like a sine wave that has been stretched in some parts or compressed. So a Fourier transform is a different way of representing the wave. Instead of using an amplitude versus time graph, the Fourier transform shows the amplitude versus frequency graph. So on the left, we have a signal with the time domain, and the right shows a Fourier transform. After the Fourier transform is complete, features are extracted, and this is what is used to train the model. So why we did not use the Fourier transform in our final model? So unfortunately, no matter how much we modified the model and changed which features to extract, the accuracy stubbornly stayed at 82.77%. And in fact, this percentage is about the same as the number of zeros or normal ECGs in our original data. So we suspect that our model simply was guessing zero for every validation case. So splitting the data and normalization. Instead, we've decided to focus on the data points themselves since the Fourier transform was not performing very well. So here for data processing, the original data was already divided into training and testing. So we further divided the training data into training and validation. And the training data is used to create the classification model. The validation data is used to evaluate the model accuracy. And finally, the testing data is used to test the model on data it hasn't seen before. So for the data we used in our neural network, we also shuffled and stratified the data while we split it. The X values were then reshaped to fit the neural network, and the Y values were changed to categorical.
Our team actually ended up trying a number of different models in our search for the best classifier. And the first one was a logistic regression model, which is fairly basic and determines the probability of a certain class existing. To see if the model worked, we used a number of different metrics, such as the accuracy, which were both around 91%. It seemed promising. However, another metric called the ROC curve showed that the actual arrhythmias, the orange, green, and red lines, were not being accurately classified. The closer the line is to the top left corner, the better. The area under the ROC curve, which was about 0.95, was close to 1, which is our goal. When you look at the confusion matrix, it shows a similar story to the ROC curve. The normal heartbeats, which are at the top left corner, were being correctly classified. However, we still had work to do to classify all of the actual arrhythmias.
So next we tried the support vector machine, or SVM, and this will find the hyperplane that will effectively classify the data points. This means the model will attempt to divide points to different labels, while also maximizing the distance from the plane to the nearest data points. So the SVM had a higher accuracy than our logistic regression, with validation and test accuracies just under 97%. The confusion matrix shows that the squares with the predicted values matching the true value are darker, and this is good. This means that there's very little false positives or false negatives. The ROC curve is, the area under the ROC curve is 0.979, which is really close to the target value of 1.
Next, we have nearest neighbors, and this basically classifies as based on the nearest k data points. So our confusion matrix, once again, is able to strongly classify normal beats compared to the logistic regression and SVM. Nearest neighbor has a better chance of accurately classifying the data.
The next model that we use is a random forest model. So random forest model is a model in which series of decision trees are utilized to train and identify the given data. Decision trees, as it's described in the image on the right side, is a model in which data are classified into numerous subclasses to precisely interpret the data and use it for our training. And the result that we got from the random forest model was as follows. For the validation accuracy, the random forest model had an accuracy around 97.56%, which was slightly yet significantly higher than the 3 previous models. With accuracies above 97%, the model showed great accuracy in general.
So since all of our models so far were performing pretty well and only missing a few percentages in the accuracy, we decided to try the voting classifier to see if the majority vote between these 3 models would help out. So unfortunately, we weren't able to bridge those last few percentages to reach 100%, and the accuracy stayed about the same.
We knew that to fully optimize our classification process, we would have to use a neural network. And since the neural networks are based on the nervous system, they're a bit more involved than previous models. They contain layers that determine the most important parts of the input data in order to identify and correctly output their classification. And we tried many different things, such as changing the layers, optimizers, batch size, and everything in between. key was to find a balance between all these parameters. If the model is too accurate to the training data, it will become overfit and be unable to classify new data. Too broad, and the model will be underfit and won't correctly classify any data. So our goal is to find the optimal model that had the best area under the curve while also minimizing loss or the margin of error.
So for our final model, we used sequential as our main model, added layers of dense and conv 1D with activations of tanh and relo respectively. We also flattened the data to preempt potential dimension-related problems and a dropout layer to prevent overfitting. The result of the neural network is as follows. We had a 98% validation accuracy with a model loss of 0.132.
Our confusion matrix shows that the classifications of class 0, 2, and 4 are highly accurate, while 1 and 3 still need improvement. This is indicated through the shading of each box, and through this confusion matrix, we can also see an issue. So currently our data is highly concentrated in class 0, or normal beats, which is a limitation when we're working with this data set. We can assume that the accuracy of 1 and 3 were low due to insufficient data given for these classes. Here we can see that the ROC curve reflects what we saw in the confusion matrix. Class 0, 2, and 4 seem to have a high accuracy, whereas class 1 and 3 fall short, although they did better than our previous models. The area under the ROC curve was the highest for any model, which was 0.988, meaning that the model was the closest to reaching our goal of 1.
So finally, the results and conclusion of our final project. The result, specifically the 98% validation accuracy from the neural networking, was significant because the high accuracy of our model is directly related to the effectiveness of the model in the real medical background. The higher the accuracy, the more effective the model will be to spot arrhythmia and prevent potential heart failures, which would then result to saving more lives with this model at the very end of the day. And our team's goal for this project at the very end of the day and from the very get-go of this project was to embody the Medlytic course's aims, which was to use machine learning in areas of medicine and healthcare. That is why our group didn't limit ourselves to the boundaries of BWSI and this specific presentation. We reached out to clinicians and professors who work in the medical field and or data science to not only receive their comments, but also to have our model used in the real world with real patient data. And as we receive more feedback and more data from the experts, our group hopes to not only strengthen our model's precision, but to have this model to aid and impact people's lives by classifying their heartbeat and knowing whether they have arrhythmia or not. That's the end of our presentation, and thank you so much for your time.
Thanks, Brian. Thank you. Our final team. Everyone, we have, it looks like our hard cutoff is 11:54, so we have a lightning round of 2 questions for each team, perhaps, if we can do them quickly. Let's see what we can have.
Yeah, so I think for the first team that just presented before then, so Vivian, Lucas, and Jiwoo, and the rest of your team, I just want to ask, like, what process did you take in building the model to determine like the sentence length that you use in training and the testing set?
So we Lucas, you want to answer?
Yeah, sure. So during the process, we basically first fed it through a tokenizer, which would turn each word into a specific number. And then we'd fed it through an embedder, which would turn those numbers, or at least trained over time, to give a specific vector, which once trained, all those vectors would be grouped together into certain sentiments, allowing the model to, understand words based on their meaning, not based on their spelling necessarily. And I think that after that, we built up a model based on a densely connected network, which would use training weights in order to slowly classify each transcription into a certain class. Yeah.
Thank you, Lucas. And thank all of you. We've hit 54. I don't know if MIT video is about to cut us off. Yes, all right. Yes, all right, everyone. Thank you so much. I'm sorry, we don't have any, if anyone wants to type questions into the chat, that will work as well. But MIT AV is going to cut us off, so we are hitting up the end. We will see you all at the rest of the event, main event.